Hello friends, I am Pankaj and in today's session you will learn about the concept of queuing theory. Before you start listening to the session, please keep aside your mobile phone, preferably keep it in a silent mode. Believe me, it will help you to understand better. I assume that pen and paper is with you. If not, go get them first. You cannot learn topics of optimization techniques simply watching a video without noting down the important points and concepts. Plus, we'll be doing numerical. Okay, so now that you are ready, let's start the session by asking what queuing theory is all about. To begin with, we can say queuing theory, which is also known as the waiting line theory, deals with the different aspects of formation of a queue. Before discussing these different aspects, we'll first focus on the meaning of a queue. As such, we all know the meaning of a queue. However, to make sure that we all have the same and right understanding of the term, we'll define the term queue. Queue simply means a sequence of people, work, vehicles, or any other entities or subjects awaiting to get the service or to be processed. When a queue is formed, what is the reason behind formation of a queue? A queue is formed when the number of customers arriving is greater than the number of customers being served. A queue is formed when the number of customers is more than the number of servers and there is a lack of perfect balance between the entities who need the service, commonly referred as customers, and the entities who provide the service, commonly referred as servers. Formation of queue is quite common in our day-to-day life. You all have experienced that. You have experienced queue during lunch hour when you go to canteen, in accounts department while paying the fees, in metro station, in petrol pump, and the list is endless. But why it is important to know about queuing theory? Why we are studying queuing theory? When you stand in a queue for a long period of time, we not only get annoyed, we also waste considerable amount of time. The amount of time population of a country wastes by waiting in queue is a major factor influencing quality of life in the country and also the efficiency of a nation's economy. Think of the loss in production when machines wait to be repaired, the loss in business due to delay in subsequent shipments when trucks and ships wait to be unloaded. Imagine the wastages of fuel that take place when planes wait for their turn to land. Even in IT and telecommunication, we see data glitches and delays due to saturated lines. The point is, if the number of customers are too big compared to the number of servers, queue will be formed and there will be wastage of time and resources. So what is the solution? Now you can suggest we should create more and more servers compared to the number of customers. And when you do so, there is no question of formation of queue. But there's a problem with this idea. We cannot get our servers free of cost. We need to invest our resources and not necessarily throughout the day the number of customers will always be more than the number of servers. For example, when you go to a metro station in the morning or evening peak hours, you find a queue. But in the same metro station, the servers, that is the entry points, remain idle in the afternoon. So simply creating more and more servers compared to the customers is not the solution. It will simply lock up your resources. Then what is the solution? The solution is we need to find a balance between the number of customers and the number of servers. The knowledge of queuing theory help us in attaining that balance. Now that we have understood the meaning of queue and the purpose of studying queuing theory, we'll focus on understanding the basic structure of a queuing system. The queuing process assumed by most queuing model is shown in the next slide. As shown in the diagram, in a basic queuing process, customers requiring services are generated over time by an input source. These customers enter the queuing system and join a queue. After the customers join the queue, they are selected for service by some rule known as the queue discipline. The required service is then performed for the customers by the service mechanism, after which the customer leaves the queuing system. So a basic queuing system can be described by its components. Mainly, input source, customers, queue, service mechanism, and the outgoing served customer. Okay, next we'll learn about these components, the alternative assumption that can be made about these elements of the queuing process. The arriving unit that requires some kind of service is referred as customers. The customers may be people, machines, vehicles, or any other entity that need to be processed or served. The population from which the customers arrive at the queue is referred as the input source or calling population. Input source is classified based on its size, that is, on the basis of total number of customers that might require service from time to time. Depending on the size, we classify input source into two types, infinite and finite. For example, in a railway reservation counter, where anybody can come and join the queue, the input source is considered infinite. But an office canteen, which is not accessible to the outsiders, the input source is considered finite. Why it is necessary to classify population as finite or infinite? We classify the input source because the size of the input source makes a difference to analysis and calculation. But before we answer how the size affect the analysis, now let's first understand on what criteria we classify the population as infinite and finite. An input source is considered infinite if the rate at which the input source generates new customers do not get affected by the number of customers in the queuing system. The number of customers in the queuing system means the sum total of customers who are in the queue as well as those who are being served at that point of time. For an infinite population, the number of customers who are in the system do not influence the arrival rate of new customers. On the other hand, an input source is called finite or is referred as finite if the rate at which the input source generates new customers is significantly affected by the number of customers in the queuing system. That is, for a finite population, the arrival rate of new customers is significantly affected by the number of customers in the queuing system. The fact that in finite population, the number of customers in the queuing system affects the number of potential customers outside the system at any time makes the finite case more difficult to analyze. So to answer the question that how size of the population affects the analysis, we can say that our calculation and analysis become easier in an infinite population compared to a finite population case. Before we move to discuss the other components of queuing system, we'll talk about two things related to what we have discussed so far. The behavior of the customer and the distribution of arrival time of customers from the input source. First, we'll talk about the behavior of the customer. Customers, when they come to join a queue, may behave in four different manners. In the first category, we have customers who refuse to join the queue because the queue is too long and he or she has no time to wait or there is no sufficient waiting space. This kind of behavior is referred as bulking. This kind of behavior we can observe in a CNG station or in a departmental store when there is a big queue. In the second category, we have customers who wait for some time in the queue but leave suddenly when the patients get exhausted without getting the service. This behavior is referred as reneging. This kind of behavior also we can observe in a departmental store when the customer finds that the salesmen are taking too long a time with other customers and a big number of customers are ahead of him or her. In the third category, we have those customers who jumps from one queue to another to improve their position and get faster service. This behavior is termed as jockeying. This kind of behavior we can observe in metro station, toll plaza, and even in departmental store. As one queue moves faster, people from other queue jumps to that if it helps them improve their position. The next category, we have customers who wait in the system voluntarily or involuntarily until served. No matter how long they have to wait. For example, when machines move to an internal maintenance setup for repair, they exhibit behavior of a patient customer. Besides the above four, we can observe another situation where some customers get preference over other. For example, in an emergency situation in a hospital, we see this kind of behavior. Next, we'll talk about arrival time distribution. Before we know what kind of priority distribution arrival time follows, we'll understand what is arrival time and why it is important to know about arrival time distribution. Arrival time, or to be precise, inter-arrival time, is the time gap between two successive consumers joining the queue. Why it is important to know about arrival time distribution, how it helps in our analysis. The priority distribution of arrival time along with the priority distribution of service time determines the operating characteristics of a queuing model. I repeat, the priority distribution of arrival time along with the priority distribution of service time determine the operating characteristics of a queuing model. Let's not bother about the meaning of service time or what are operating characteristics. We'll discuss this afterwards. Here we focus on understanding what kind of priority distribution arrival time follows. We know in a queuing system, the input source generates the customer. This generation takes place in a random manner. Or to say it alternatively, randomly the customers come from the population to join the queue. There are time periods when relatively more customers join the queue, and then there are time periods when relatively less customers join the queue. But the assumption that we make in queuing analysis, over a period of time, the average rate at which customers join the queue remains fixed. Over a period of time, the average rate at which customers join the queue remains fixed. This is regardless of how many customers already there. Why we are making this assumption? How this assumption is going to help us? The sole purpose of making this assumption is to keep our analysis mathematically easy to handle. And there are two priority distributions related to this assumption. One is Poisson distribution and the other one is negative exponential distribution. In queuing model, we assume that the arrival pattern of the customer follows what is known as Poisson probability distribution. If we denote the customer's mean arrival rate per unit of time, say an hour, as lambda, then this is how we can write the Poisson probability distribution. Here n stands for the number of arrival in an interval. If lambda is the average arrival rate of customer, then the inter-arrival time between customers will be 1 upon lambda. Is that okay? Can you follow that? Let's take an example. If in an average per hour 6 people join a queue, that is in 60 minutes 6 people join a queue, then we can say every 10 minutes 1 person join a queue. This gap is the inter-arrival time and can be written as 1 upon 6. Similarly, when lambda is the arrival rate, then 1 upon lambda will give us the inter-arrival time. There is a relationship between probability distribution of arrival time and probability distribution of inter-arrival time. If the arrival rate follows Poisson distribution, then the inter-arrival time follows negative exponential distribution. To be more precise, if the number of arrivals of customer follow Poisson distribution with a mean rate of lambda, then the inter-arrival time follows negative exponential distribution with a mean of 1 upon lambda. So when you say customer arrival follow Poisson distribution, it is equivalent to saying that the inter-arrival time follow negative exponential distribution. Some of you must be wondering about the form of negative exponential distribution. We are yet to learn about the form. We'll talk about this when we go to the service time, when we discuss the service time. We now focus on understanding the next component in the basic queuing structure. We know queue refers to those customers who are waiting for service and does not include the customers being served. Depending on the maximum permissible customers in a queue is classified into two categories, infinite and finite. In infinite queue, any customer who comes to get the service may join the queue, and there is no restriction on the number of customers who can join a queue. While a finite queue implies a restriction on the number of customers in a queue. In a finite queue, we restrict the queue length to a certain limit, and once that limit is reached, customers are not allowed to join the queue. For example, think of a garage with a single mechanic and limited space for vehicles. If the garage has space for say 10 vehicles, then we can say that the queue length is 10. The first 10 customers can park their vehicle for service, but the 11th customers cannot park his vehicle for service. That is, he cannot join the queue. There is one important point that we need to remember about the queue length or size. Most of the queuing models is based on the assumption of an infinite queue length. Even for situation where a queue length is finite but allows a relatively large number of customers, we consider the queue length as infinite for all practical purposes. An aspect related to queue is queue discipline. The queue discipline refers to the order or the rule according to which customers form a queue are selected for service. The most commonly used rules of selection are first in, first out, or first come, first served, first in, last out, selection in a random order, selection on a priority basis. All of these are quite self-explanatory, so I'm not going into detail of these rules of selection. The point that we need to remember is, unless otherwise stated, the implicit assumption of a queuing model is first in, first out, or first come, first served. The last component of the basic queuing structure is the service mechanism. Service mechanism is an arrangement that exists to serve the customers. This arrangement depends on the number of channels or facilities that are there to provide the service and in how many phases the service is provided. There can be single channel or single facility to provide the service, or there can be multiple channel or multiple facilities to provide the service. To understand the difference, think of the payment facility in a small retail store and a big departmental store. In a small retail store, usually there is a single payment counter and everybody need to make the payment for their purchase only at that counter. Whereas in a big departmental store, a number of parallel payment counter exist and a customer can make the payment at any one of them. The retail store is an example of single server or single channel, while the departmental store is an example of multiple server or multiple channel. The other thing that determines the service mechanism is the number of phases the customers need to go through to complete the service. To understand the difference, think of the service mechanism in a toll plaza and the service mechanism in a hospital. In a toll plaza, a person needs to make a payment at a single point and continue the journey. But in a hospital, to get the service, one needs to go through a number of phases. First, the person will register, then make the payment, consult the doctor, go through the test and checkups prescribed, take the report, meet the doctor again, buy the medicine, and then the service is completed. The scenario at a toll plaza is an example of single phase, while the hospital situation where the customers need to go through a series of steps in sequence is an example of multiple phase. The service pattern can have different combination of channels and phases. It can be single channel, single phase. For example, the payment facility of a small retail store having only one counter. The service pattern can be multiple channel, single phase. The payment facility in a departmental store having a number of counters is an example for that. It can be single channel, multiple phase. For example, the semester registration process in a college. Students need to go through a number of steps like filling the form, get it signed by different departments like accounts, library, and then deposit it in the register office. The last one is multiple channel, multiple phase. The service mechanism in a big hospital where there exists a multiple counter for registration and fee payments can be considered as an example for this. Another related aspect to service mechanism is the concept of service time or holding time. Service time refers to the duration from beginning of service till the end of the service. Simply put, it is the time required by the server to complete the service for a customer. Service time is important because the probability distribution of the service time along with that of the arrival rate of customers determine the operating characteristics of a queuing model. The service time distribution that is most commonly assumed in queuing theory is the negative exponential distribution. If the mean service rate per unit of time is mu, then this is how we can express the negative exponential distribution. Operating characteristics are the different attributes of a queuing system, and a clear understanding of these concepts is necessary to analyze queuing models. The first two operating characteristics that we will discuss is arrival rate and inter-arrival time. We already have some idea about these two, but let me explain again. Mean arrival rate is the average number of customers who joins the queue from the input source. It is usually denoted as lambda. Suppose in 1 hour or say 60 minutes, in an average 5 customers join a queue, then lambda is 5. The point to understand is if in an average 5 customers join the queue, then the average interval time between successive customers will be 1 upon 5 hour or 60 upon 5 minutes. That is 12 minutes. That is, on an average, after every 12 minutes, a customer joins the queue. This is termed as the mean inter-arrival time. So if lambda denotes the mean customer arrival rate, then 1 upon lambda denotes the mean inter-arrival time of customers. In the same fashion as mean arrival rate and mean inter-arrival time, we can define mean service rate and mean service time. Mean service time refers to the number of customers that get served by the server per unit of time, while mean service time refers to the average time that is needed per service. For example, if mu, which is usually used to denote the service rate, average service rate, is say 6, that is in an hour or 60 minutes, 6 customers are served, then the average time required to serve a customer is 1 upon 6 hour or 60 upon 6, that is 10 minutes. So if we use mu to denote the mean service rate, then 1 upon mu denotes the mean service time. Traffic intensity is also known as service utilization factor. It tells us about the fraction of time the server is busy. We can find the fraction of time the server is busy by dividing the mean service time by the mean inter-arrival time of customer. The mean service time is 1 upon mu, while the mean inter-arrival time of customer is 1 upon lambda. On simplification, we get the traffic intensity value as lambda upon mu. It is denoted as rho and the unit is termed as Erlang. 1 minus rho tells us the fraction of time the server is idle. There is one important point that I want you to note. The value of lambda is always less than the value of mu. That is, lambda upon mu is always less than 1. Why it has to be so? To understand what will happen if lambda is more than mu, let's take an example. Say lambda value is 6 per hour, that is per hour in an average 6 customers join the queue, and the mu value is 5 per hour, that is every hour 5 customers are served. Note, every hour 6 customers join the queue and only 5 customers leave the system after being served. As a result of this, the queue length will go on increasing, meaning some people in the queue will never get the service. This is especially true for infinite queue length. In case of finite queue length, lambda may be greater than mu. Since there is a restriction on entry of new customer, everyone in the queue will get the service. Next, we need to know about the queue length, system length, waiting time in queue, and waiting time in system. Queue length refers to the average number of customers in the queue to get the service, while system length refers to the average number of customers in the system. That is, the sum total of average customers who are in the queue and the average number of customers who are getting served. Waiting time in queue refers to the average time the customers have to wait in the queue before the service starts, while waiting time in the system refers to the average total time the customer spent in the system, first in the queue and then in the server getting the service. That is, waiting time in the system is the time spent in the queue plus the time spent getting the service. The status of a queuing system can be in two conditions: transient state condition and steady state condition. A queuing system is said to be in transient state condition when its operating characteristics are dependent on time, while a queuing system is said to be in a steady state condition when its behavior or operating characteristics are not dependent on time. When a queuing system starts its operation, the system is considered in a transient condition. However, after a lapse of sufficient time, the operating characteristics become essentially independent of time and the system reaches a steady state condition. In our analysis, we consider the queuing system to be in a steady state condition. The transient case is more difficult analytically. All the operating characteristics and notation that we define is based on the assumption that the system is in a steady state condition. There exists a number of different queuing system models. These models are classified depending on the number of channels, priority distribution of the arrival process and service process, queue discipline, queue length, and population source. To describe the models, we use something known as Kendall's notation. In Kendall's notation, each letter specifies one particular aspect of the model. Mostly 6 letters are used, but sometimes 5 letters are also used. The first letter A defines the priority distribution of the entire arrival time. The second letter B defines the priority distribution of the service time. The third letter C defines the number of parallel servers or channels that is there in the system. The fourth letter D specifies the queue length, whether it will be finite or infinite. The fifth letter E specifies the queue discipline. The sixth letter F specifies the population source. There are two important points that we need to note. First, not always all the 6 letters are used to specify a model. As already pointed out, sometimes the model is specified using 5 letters, sometimes even with 3 letters. Second, besides the first 2 letters, which always specify the arrival distribution and service distribution, the specification of the remaining 4 letters are not always fixed. It changes from author to author. For example, one author may use the 4th letter to specify the queue length and the 5th to specify the population source, while another author may use the 4th to specify the population source and the 5th to specify the queue discipline. Using the notations, this is how we can write the different queuing models. However, we limit ourselves in understanding the first model. The first model represents a single channel, single phase system where the queue length is infinite, the customers are served on first come first served basis, plus the arrival process follows a Poisson distribution while the service process follows a negative exponential distribution. We have specified this model through 5 letters. The first letter specifies the arrival process while the second letter specifies the service process. We know arrival process follows Poisson distribution while the service process follows exponential distribution. As you can see, we have used the same letter M to characterize both the cases. Why so? Both Poisson and exponential distribution exhibit something known as Markovian property or memoryless property. So instead of writing Poisson and exponential distribution, traditionally both are specified as M, which implies the Markovian property that this distribution exhibits. What is this Markovian property or memoryless property? Discussing this in detail is beyond our scope, but in a very simplistic manner, we can say that as per this property, the queuing system does not have any memory. Or in other words, the system does not take into account the previous state to define the present state. The third value 1 specifies that there is a single server or single channel. The fourth term, infinity, indicates infinite queue length. The last term of the model implies that the customers are served on first come, first served basis. Next, we learn about how to find the different measures of this model 1. For this, we'll first derive something known as steady state equation. Let's suppose that P suffix n t plus h denotes the probability that there are n customers in the system at time t plus h, where h denotes the very small time period. There are 2 points to note. I've said there are n people in the system. Hope you remember the difference between system and queue. And the second thing, and the more important thing, I've said h to be a very small time period. Question is, how small is h? We make an assumption that h is such a small time period that only one event, either an arrival or a service, can occur. Both arrival and service cannot take place in the time period h. Now the question is, in how many ways there can be n people in the system at time t plus h? As per our assumption of h, that only one event can occur, there are 3 possible ways of having n people in the system at time t plus h. Take your time and go through these 3 scenarios. You can see in every situation there are n number of people at time t plus h. Just note, since we have assumed h to be a very small time period where only one event can occur, either an arrival or a service, hence we have ignored the possibilities like 2 arrivals and 2 service, and so on. As you can see, the probability of n people at time t plus h can be expressed as the sum of 3 situations. The first part in the right hand side, shown in blue, gives the product of 3 things: probability of n people in time t, probability of no arrival in time h, and probability of no service in time h. The second part, shown in green, shows the product of probability of n minus 1 people in time t, probability of 1 arrival in time h, and probability of no service in time h. The last part, shown in red, shows product of probability of n plus 1 people in time t, probability of no arrival in time h, and probability of 1 service in time h. The sum gives the probability of n people in time t plus h. If arrival rate per unit of time is lambda, then using basic probability concepts, we can denote the probability of one arrival in time h as lambda h. Consequently, the probability of no arrival in time h can be denoted as 1 minus lambda h. Similarly, if the service rate per unit of time is mu, then using basic probability concepts, we can denote the probability of one service in time h as mu h. Consequently, the probability of no service in time h can be classified as 1 minus mu h. Substituting all this in the expression of probability of n people at time t plus h, we get simple algebraic manipulation gives us the third line shown in bold. I hope all of you can follow the calculation. Now, as we are interested only in time period h, and not in the higher order, that is h square, so we will ignore all the higher order terms in this expression. Then we get the simplified expression for probability of n people in time t plus h. Some simple algebraic manipulation take us to the last line. Here, when h tends to 0, the expression pnt plus h tends to pnt. This makes the left hand side of the expression equal to 0. Again, few simple algebraic manipulation give us the equation number 1. This equation number 1 is the first steady state equation. But to get the second steady state equation, we need to find the probability that there are 0 people in the system at time t plus h, where h again is a very small time period. Just like our previous case, the probability that there are 0 people in the system at time t plus h can be expressed as the sum of two situations. In the first situation, there is 0 people in the system at time t, and without any arrival and without any service in time period h, there is 0 people even at time t plus h. In the second scenario, there is 1 people in the system at time t, and with no arrival and only one service in time period h, there is 0 people in time t plus h. The probability of n equal to 0, that is the probability of 0 people in the system, is expressed as the sum of two situations. Assuming that the arrival rate is lambda and the service rate is mu, we need to find the different probability values in time period h. If the arrival rate is lambda, then the probability of one arrival in time h is lambda h, and the probability of zero arrival is 1 minus lambda h. Similarly, if the service rate is mu, then the probability of one service is mu h. These three expressions are similar to what you have learned in the previous case. But the probability of no service in time h when there is no arrival is not 1 minus mu h. The probability of no service when there is no arrival and 0% in the system is certain, and it is equal to 1. Substituting the values and doing simple manipulation give us the last line. As we are interested in time period h only, hence ignoring the higher order cases containing h square, we write the expression. Simple manipulation give us the last line. Here, when h tends to 0, the expression p naught t plus h tends to p naught t. This makes the left hand side of the expression equal to 0. Simple manipulations give us the second steady state equation. These two steady state equations help us in deriving the different measures related to a model. The 10 most common measures related to model 1 are shown in the next slide. We'll first talk about how to determine the probability that there exists n units in the system. To determine the probability that there exists n units or customers in the system, we start with the two steady state equation. Just to simplify the notation, we remove the term t from the equations. Simple manipulation of equation 2 gives the probability that there exists one customer in the system as lambda upon mu into p naught, and taking n equal to 1 in equation 1, we get the last line. We break the equation obtained from the last line of the previous slide and then do some simple manipulations. In the fifth line in green, we put the value of p1 obtained from equation 1. Some more manipulation give us the expression for p2. In the same fashion, we get the expression for p3. Then we generalize to get an expression for pn. Here we want to find the probability of no customers or units in the system. We start with the fact that the sum of the probability is equal to 1. We replace the probability value of 1 unit, 2 units, 3 units by the expression B obtained from the previous slide. Some simple manipulation give us the P naught value, that is the probability of no customers in the system. Here also we get another expression for finding probability of n customers in the system. We have replaced lambda upon mu as rho in the last line marked as green. Here we are finding the mean number of customers in the system. The starting point is the concept of expected value of a probability distribution. After doing some manipulation, the final expression is shown in green. In this slide, we are finding an expression for the mean number of customers. Both expressions C and D can be used to determine the mean number of customers. This slide gives the expression for three things related to the model: the variance of the number of customers in the queue, the average time the customer need to spend in the system to get the service, and the average time customer need to spend in the queue before getting the service. This slide provides four measures related to model 1. The first measure tells us the probability of the number of customers in the queue being greater than equal to a certain value k. The second measure tells us the probability of the number of customers in the entire system being greater than a certain value k. The third measure, marked as 9a, tells us the probability of a non-empty queue. It is important to note that even when there is one unit in the queue is considered non-empty. The last measure tells us the probability that a customer will spend more than t time in the system for getting the service. The last point of discussion in this session is the relationship between number of customers and the waiting time. These relationships were given by John Little and is popularly referred as Little's law. L suffix x gives the average number of customers in the entire system, while Ws gives the average waiting time of the customers in the entire system. And as shown, Ls is equal to the product of arrival rate lambda and Ws. In this slide, we show the relationship between LQ, the average number of customers in the queue, and WQ, the average waiting time of the customers in the queue before the start of the service. And as shown, LQ is equal to the product of arrival rate lambda and WQ. This slide shows the relationship between LQ and LS. And LS is the sum of LQ and the rho value, which stands for traffic intensity. This slide shows the relationship between waiting time in queue and waiting time in system. Waiting time in system is the sum of waiting time in queue and 1 upon mu. Mu stands for service rate, so 1 upon mu gives us the time spent while getting the service. So waiting time in system is waiting time in queue plus the service time. Okay, so we'll end the session here. In this session, we have tried to cover the basics of queuing theory and model 1, which is the most important model from our exam point of view. Once you become comfortable with the theoretical part, we'll have a session for the numerical related to model 1 and second of the remaining model, which is also part of our curriculum. Okay, but before that, you first go through this video again, make yourself comfortable with these concepts. For any queries, doubts and questions, feel free to contact me through my WhatsApp number. If you want, you can also send me an email. So looking forward to your feedback, suggestion and comments. Happy learning and all the best.